My name is Srdjan Kitic of Orange Labs France, and I will present joint work with my colleague Jérôme Daniel titled Eco-enabled direction of arrival and range estimation of a mobile sound source in ambisonic domain. Our goal is to show that acoustic reverberation and particularly early echoes actually contain useful information and as such should not be considered a flaw, as usually considered in acoustic signal processing. Why should one care about it? Well, it's because it can enable a number of interesting applications, including room geometry estimation, source localization behind soundproof obstacles, matched filtering or acoustic rake beamforming, robot navigation, spatial audio coding, spatially enriched communication services, and many more. In order to benefit from early reverberation, one needs a method to extract spatial temporal information encoded in acoustic echoes. This is not an entirely new problem, and a lot of research effort in the last decade or so has been dedicated to its solution. In most cases, strong assumptions have been put in place, such as the availability of recorded room impulse responses, or the knowledge of source signal, source position, or the time of arrival. There are also methods that exploit other modalities in addition to sound, such as video, laser, LiDAR, etc. We set a somewhat ambitious goal. We would like to extract the spatial temporal information only from the observed microphone area recordings without any prior information or other modalities. In this work, we use Ambisonic spatial audio format, which is well suited for acquisition, rendering, and playback of 3D sound scenes. Multi-channel ambisonic signals constitute an intermediate representation, sitting between sound capture and playback. This is an important advantage since once the appropriate linear encoder and decoder have been applied, the ambisonic format becomes theoretically agnostic with regards to the actual recording and reproduction systems. At the heart of the ambisonic format is the decomposition of acoustic pressure field onto the basis formed by spherical harmonic functions. In practice, spherical harmonic decomposition is truncated, meaning that only the coefficients up to some maximal order are retained. First order ambisonic, or FOA, keeps only 4 channels. Alternatively, higher order ambisonics, HOA, these signals have more than 4 channels. One can think of ambisonic channels as the result of probing the acoustic field by a collection of spatial filters, each having a particular spatial response. For example, the first FOA channel, often labeled by the letter W, corresponds to the omnidirectional filter. The remaining 3 channels, X, Y, and Z, are akin to figure of 8 directed microphones, aligned with coordinate axes. Another important characteristic is that all channels are in phase, meaning that the wavefront coming from a distant source in free field reaches all ambisonic channels simultaneously. Hence, in frequency domain, ambisonic channels can be represented by a spatial encoding vector, which depends solely on the direction of arrival of the wavefront, modulated by the delayed and attenuated source signal. In a more general case, the received signals are simply the superposition of weighted plane waves, denoted here by the encoding letters YN, multiplied by the source component SF. The complex weights gamma n encode the attenuation and delay of a given plane wave relative to the direct propagation wavefront. In a recent work, we have used the ambisonic representation to define so-called generalized velocity vector. In frequency domain, this is the ratio between ambisonic channels, denoted here by the vector B, and the reference signal, which is just a linear combination of all channels. In practice, the reference signal is usually beamformed towards a rough estimate of direction of arrival, for the reasons that will soon become clear. We remark that this is a generalization of relative transfer function in ambisonic or spherical harmonics domain, which is also found in the literature as relative harmonic coefficients. Importantly, this representation is free from the source signal contribution, and therefore characterizes only the spatial properties of the acoustic environment. Obviously, generalized frequency domain velocity vector is not identical to acoustic transfer function. Even in free field conditions, the information about absolute delay or time of flight of the signal is lost. Accordingly, we have defined generalized time-domain velocity vector, or GTVV, as the channel-wise inverse Fourier transform of the frequency domain version. Assuming that the beamformer is sufficiently suppressing the reflections such that their cumulative magnitude does not exceed the magnitude of a direct wavefront, the GTVV admits a very compact and informative expression. Note that one can immediately deduce the encoding the encoding vector belonging to the direction of arrival, which is at the delay 0 of GTV, and moreover the other large peaks of GTV represent other wavefronts. Position of the peak is analogous to a relative delay τn, while the corresponding vector yn encodes the wavefront direction. We have seen that GTVV can provide the wavefront directions and their relative delays. This can be thought of as the time difference of arrival between wavefronts. But to estimate the source to microphone distance, we need absolute delay, or time of flight, which has been lost when calculating GTVV. However, we will show that this information can be recovered if the sound source is mobile, meaning that it changes its position along time, while the microphone array must remain fixed. The working assumption is that the acoustic reflections are specular, which allows us to use the classical image source model for the further analysis. Let's first revisit the image source model to gain intuition how the trajectory of a mobile source and its reflections are related. Here we see a fixed microphone array depicted by a spherical microphone and a mobile sound source whose trajectory has been sampled at a finite number of positions across time. We can also see the reflected trajectory of a wall at the lower right part of the figure. Note that the reflected trajectory is a mirror image of the original trajectory. However, some of the positions are missing in the reflected trajectory. This is because for certain positions of the source, the reflection becomes invisible from the microphone point of view, as the visual path is outside the panel boundaries. Now, note that the overall shape of the trajectory is preserved for any reflection order. For instance, the second order trajectory can be represented as the first order trajectory reflected off a virtual panel, which is just the symmetric extension of the second wall. Basically, the same principle extends to the third, fourth, and any other order reflections. Now, it should be intuitively clear that the trajectory of any order is obtained by an affine transformation of the original trajectory. Affine transformation can be either reflections, rotations, or translations, or combinations thereof, and are often used to describe the motion of a rigid body. Therefore, the key property of affine transformation is that they preserve Euclidean distances between any 2 points over trajectory, which is an important constraint that we will use to estimate the distances between the microphone and each source position across time. Now, let's focus to any 2 different positions or any 2 points of the trajectory. For simplicity, assume that each position corresponds to a frame of a multi-channel ambisonic recording. Recall that the information obtained from the GTV representation at some frame denoted here by K is the direction of arrival, represented here by a unit vector U0, and the directions and relative delays of any particular nth reflection, denoted here by Un and τn respectively. The goal is to estimate the distance at each corresponding frame, which is analogous to the absolute delay τ bar, provided that we know the speed of sound, or that we can approximate it. From the figure on the right, we can express the position vectors of the source and its image by the vectors r0 and rn, and both of these contain the missing τ bar value. We are now ready to use the distance preservation property for any 2 frames k, k prime. The square magnitude of the displacement of the source and its image should be equal. Now, once we plug the expression for position vectors in the equality, we end up with a homogeneous equation containing constant, linear, and bilinear or cross terms τ bar. And τ bar, of course, are the absolute delays. Note that we can form such an equation for every reflection n and for all available combinations of frames k, k prime. Remark also that this requires labeling the corresponding directions un and the delay τ n across time. In other words, we need to track the reflections as if these are true sources. Now we can collect all or a subset of these equations and form a system. For example, should we have only 3 frames P1, P2, P3 and 2 reflections, for instance N1 and N2, we would end up with a bilinear system that looks like this. M is the matrix of coefficients that depend only on quantities inferred directly from GTVV. Rho is a bilinear mapping from a vector of absolute delays to a bar, while kappa is a constant vector. Since the system is already determined, all but nonlinear due to the nonlinear mapping rho, we will instead minimize certain loss function. We choose the L1 norm, which is more robust than the squared loss to inaccuracies in the system. And we further add a regularizing term to promote smoothness of the trajectory. The regularizer is thus the squared norm of the gradient of the vector τ bar. Note that this is a non-convex problem due to the nonlinear mapping rho, and it can also be of a large scale depending on the number of refractions and positions considered. However, the coefficient matrix M is usually very sparse, as each row contains only 3 non-zero coefficients. We test the proposed method on the real recordings taken from the localization and tracking challenge Locata Task 3. The test dataset contains 6 recordings, each having a duration between 20 and 30 seconds. This is a rather realistic setup, since the recordings have been taken in the environment whose acoustics is complex, as it contains planar and non-planar reflectors, spectral and non-spectral reflections. The sound source is a walking person who is not always facing the microphone, the speech is intermittent, and there are ambisonic encoding artifacts due to microphone array imperfections. This all means that the direction and even estimation errors are likely to occur. Furthermore, we have used an off-the-shelf voice activity detector and tracker, generally used for tracking independent sound sources. Despite all these inaccuracies, the obtained results are very encouraging, with the best median per frame range estimation error slightly above 30 centimeters, whereas the average distance of the source is between 2 and 3 meters. Likewise, the DoA estimation error per frame is small, about 7 degrees for azimuth and 5 for elevation. To conclude, we are convinced that eco-aware processing has a lot of potential to address novel and challenging use cases. We have also confirmed that GTVV is a useful tool for the blind analysis of acoustic environments, which has been showcased on the task of full 3D sound source localization. In the future, we will address new applications and use cases and further improve performance, potentially by employing learned models such as deep neural networks. Thank you for the interest in our work, and we are very much looking forward to meeting you at EUSIPCO 2022.